We're starting Unit 4, which is randomness and probability. We're specifically talking about Chapter 14, which is moving from randomness to probability. So we're first going to talk about randomness. So we have to know what a random phenomenon is. A random phenomenon is going to be random if we know what outcomes could happen, but not which particular values will happen. So, for example, coming up to an intersection. You know when you come to an intersection that the light will either be green, red, or yellow. But you don't know what color it actually will be until you actually get there. Now we need to define probability. Probability is a long-run relative frequency. So again, relative means that we're using a percentage. So it's a long-run relative frequency that an event will happen. So for example, if we wanted to know what the probability is that a coin will land heads, well, we know in the long run that's going to be 50-50 because you only have two options. If you flip a coin, you may not predict the correct outcome. It may end up being tails instead of heads, but you know that in the long run, it will be heads 50% of the time. When talking about the long run of any random phenomenon, each attempt is a trial. So every time you flip the coin is one trial. Every trial will generate an outcome. Outcomes at the end of the trial are individual possibilities. So the outcomes when you flip a coin could be heads or tails. Your actual outcome is what actually happens. Or we could roll a die. If you roll a die, you have the options of 1 through 6 showing up. Instead of individual possibilities, we may want combinations of outcomes. For example, the number on a die is less than 4. So that would be rolling a die and it coming up a 1, 2, or 3. Because 4 is not less than 4. Such combinations of outcomes are called an event. The collection of all possible outcomes is the sample space. So we're really going to focus a lot on independence within this unit. So something is independent if the outcome of one trial does not affect the outcome of another trial. So for example, when you flip a coin, it's going to be heads or tails. When you flip that coin again, what you got the first time will not have any effect on what happens the second time. Moving on to the law of large numbers. So the law of large numbers will be abbreviated LLN. What this tells us is that in the long run, the probability of repeated independent events becomes a single value or the true probability as the number of trials increases. Basically what this is saying is that if we flip a coin 10 times, we could end up getting 7 heads, which would be 70%. But if we were to flip a coin 1,000 times, odds are we'd be pretty close to 500 heads, 500 tails. Because the definition of the law of large numbers is based on repeatedly observing an event's outcome, the definition of probability is often called empirical probability. Again, I want to point out that the law of large numbers only works in the long run. It does not apply to the short term. Again, with the coin, if we flip a coin 10 times, not crazy to get 7 out of 10 heads. If you were to flip a coin 1,000 times, it would be pretty crazy to flip heads 700 times and tails only 300. Gamblers often don't follow this. They think that they're due up. Same thing with my husband with baseball. He loves baseball and he constantly thinks that a batter is going to be due for a hit if they're in the slump. And that's not true. If a batter hits 300 or 30% of the time, they still have a 30% chance of hitting the baseball. So the non-existent law of averages. Again, the law of large numbers says nothing about the short-run behavior. Relative frequencies even out, but only in the long run. So this long run is really long, like infinitely long. So this is where gamblers think that they are going to be due up, because in the short term, things don't necessarily work in the same way. Same thing with my husband and the baseball players. So if somebody's in a slump, he thinks that they're due up, but really in the long run, everything will average out. This so-called law of averages, again, it's that an outcome of a random event that hasn't occurred, has many trials, is due to occur. is not existent at all. You're never due for anything when it comes to probability. So, a question. One common proposal for beating the lottery is to know which numbers have come up lately, and then eliminate those from consideration and bet on the numbers that have not come up for a long time. Proponents of this method argue that, in the long run, every number should be selected equally often, so if they haven't come up, then they are due. So think about why this reasoning is faulty. Again, it comes down to the law of large numbers. Yes, every number is going to come up equally likely in the long run. In the short term, though, some numbers can come up more often than others. But in the long run, it would be pretty even. So we can't do this because, again, they're trying to use the law of averages, which doesn't actually exist. Things don't necessarily average out in the short term, just in the long term. So continuing to talk about probability. Due to the law of large numbers, we know relative frequencies settle down in the long run, and we can officially give the probability a value. So, which is why when we flip a coin, we know that we have a 50% chance. Or if you roll a die, you know you have a 1/6 chance of rolling a 4. For example, and I want you guys to note the notation, that P right here, capital P, stands for the probability. Then in the parentheses, we have our event or outcome that we're interested in. So the probability of flipping a coin and getting heads is 50%. Also note that the probability is written as a decimal. Probability must always be between 0 and 1. It's going to be written as a decimal. You can just move the decimal 2 places to get the percentage. So again, using that P to stand for probability, we're saying that probability is in between 0 and 1. So a probability of 0 indicates impossibility, and a probability of 1 indicates certainty. There are very few things that we know for a fact are impossible, and there are very few things that we know are certain. So odds are we will rarely ever get 0 exactly or 1 exactly, but it should be in between 0 and 1. And again, because of the law of large numbers, we would have to actually wait an infinite amount of time to make sure of an impossibility or make sure of certainty. Modeling probability. So when probability was first studied, a group of French mathematicians looked at games of chance in which all the possible outcomes were equally likely. They developed mathematical models of theoretical probability based off of this. And again, these games were definitely games of gambling because people were looking for an edge in order to win more money. And in case you were wondering, yes, that noise in the background is my son. It's equally likely to get any one of 6 outcomes when you roll a fair die. And it's equally likely to get heads or tails when a coin is tossed. However, keep in mind that events are not always equally likely. A skilled basketball player, for instance, has a better than a 50-50 chance of making a free throw. It's not just they miss or they make it. That's not how it works out. It's not 50-50. They might have an 80% chance of making it and only a 20% chance of missing. Continuing with modeling probability, the probability of an event is the number of outcomes in the event divided by the total number of possible outcomes. The outcomes that actually happen in event A divided by the number of total possible outcomes. So for example, if event A were getting heads when you flipped a coin, there's only 1 heads. There are 2 outcomes, heads or tails, so we would have 1/2. That is it for this part of Chapter 14. There's actually only going to be 1/2 of Chapter 14 left. It's a very short chapter. But I will see you guys tomorrow. I hope everybody had a great Christmas break, and I'll see you then.